Time feels like the one thing in your life that treats everyone the same. It doesn't, and right now, you are already traveling through it at a different speed than the person standing next to you. This isn't speculation. In 1971, physicists strapped atomic clocks to commercial airliners and flew them around the planet. And what those clocks recorded when the planes landed still hasn't reached most people. Satellites orbiting far above your head drift 38 microseconds out of sync with clocks on the ground every single day. Muons created in the upper atmosphere should vanish in 2.2 microseconds, yet billions of them reach the surface intact. Scott Kelly spent 340 days aboard the International Space Station and came home 5 milliseconds younger than his identical twin brother. Still standing on the ground, tonight, we'll trace that exact experiment, 35,000 feet over the Atlantic. We'll follow the line where moving forward through time turns out to be almost effortless, and moving backward turns out to be forbidden. And we'll stand at the one edge in physics where the equations allow a door backward. A door nature has never once let anyone actually walk through. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Right now, the crown of your head is aging faster than the soles of your feet. Not by much, a matter of billionths of a second, but the difference is real, and it has been measured. In 2010, physicists at the National Institute of Standards and Technology built 2 clocks so precise that a difference of 1 part in a quintillion would show up on the display. They placed one of them 33 centimeters higher than the other, about the height of a single stacked textbook, and waited. The higher clock ran faster, not because it was better built, not because of any flaw in the instrument. It ran faster because it was, however slightly, farther from the pull of the Earth beneath it. And gravity itself slows the passage of time the closer you are to its source. Your feet sit closer to that pull than your skull does, which means for your entire life, without your permission or your notice, the 2 ends of your own body have been drifting through time at very slightly different rates. Your head is always a little ahead of your feet. It has never once caught up. You've spent your whole life assuming that now is one single, unified moment, that this instant, right here, belongs to your whole body at once. It doesn't. There is no version of you that exists in only one time. There are countless versions, layered from your scalp to the ground beneath you, each ticking forward at a rate too small to feel and too real to deny. Somewhere overhead, on whatever floor holds your bed tonight, the ceiling above you is aging faster than the mattress beneath you. The difference is smaller than a heartbeat, smaller than a breath, but it does not pause for sleep, does not wait for you to notice. It has been running the entire time you have been alive. Indifferent, patient, exact. Scientists confirmed this again in 2018. With a clock precise enough to detect the same effect over a rise of just 1 millimeter. A single millimeter, roughly the thickness of a fingernail. At that scale, time doesn't behave like the steady river it feels like. It behaves more like water, finding countless separate paths down, countless separate slopes, each one slightly its own. Every added meter of height adds another sliver. A skyscraper's top floor runs measurably ahead of its lobby. An airplane cruising at altitude gains on the people who stayed on the ground below it. Little more with every hour aloft. None of these differences would ever show up on a wristwatch. They only show up on clocks built specifically to catch them, which is exactly why almost no one has ever felt them, and almost no one thinks to ask what they might add up to, over an entire life spent at the same elevation. But a fingernail's worth of drift is easy to dismiss. It's the kind of number that stays comfortable, abstract, safely locked inside a laboratory. What happens when the difference in height isn't a textbook or a fingernail, but an entire mountain and an entire lifetime? A mountain and an entire lifetime. Picture 2 sisters, born the same year, In the same hospital, minutes apart, one grows up in Leadville, Colorado, the highest incorporated city in the United States, more than 3 kilometers above sea level. The other stays in New Orleans, barely above the waterline. They live ordinary lives. School, work, children, retirement, never leaving their respective elevations for more than a vacation. By the time both women turn 80, the sister who lived on the mountain has genuinely, measurably aged more than the sister who lived at the coast, not in wrinkles or grey hair. Those tell you nothing reliable about time itself. In actual elapsed time, recorded by a clock, her particular corner of space-time moved forward faster, by a margin of roughly 90 microseconds across her whole life. Not enough to notice in a mirror, enough to prove that the ground beneath your feet has been quietly writing a different length of life for you than it writes for someone standing somewhere else. 90 microseconds sounds small enough to ignore, and for a human lifetime, it is. Imagine it anyway. Imagine feeling it, not seeing a number on a page, but actually sensing your own pace of living shift as you climbed. The elevator ride to a hotel room on the 40th floor would carry you, almost imperceptibly, into a slightly faster current of time than the one running through the lobby you just left. You would step out of that elevator having lived a fraction more than the person who stayed behind to hold the door. No sensation, no sound, just a debt, paid forward, that neither of you would ever be able to detect without a laboratory clock strapped to your wrist. Geodesists have started using this effect on purpose. A technique called chronometric leveling now measures the exact height difference between two buildings, not with lasers or satellites, but by comparing how fast identical atomic clocks tick in each location. Raise a clock by roughly 1 meter, and the shift in its ticking rate reveals the elevation more precisely than most physical surveys ever could. Time, in other words, has quietly become a measuring tape, one that reads your altitude back to you in the currency of your own aging. Scale the altitude up, not 3 kilometers, but 3,000. And the numbers stop being ignorable. Move close enough to something massive enough. And the gap between the two sisters stretches from microseconds into years, and then into something closer to forever. Gravity, it turns out, is not a force that merely pulls. It is a current that carries you through time at a rate that depends entirely on where you happen to be standing. There is a place where this effect stops being a rounding error and starts being the entire story. A place where the pull downward isn't a mountain's worth of gravity, but a collapsed stars. And where a person hovering carefully at the edge could watch an entire human civilization rise and fall on the other side, while their own wristwatch barely ticked past a single quiet afternoon. That place exists, and it has a name: the photon sphere, a narrow band surrounding a black hole where gravity curves space so sharply that light itself is bent into orbit. Just outside it lies the region physicists actually use for time dilation calculations too extreme to test anywhere on Earth. Here are the numbers, precisely, because the precision is the point. Near the event horizon of a black hole with the mass of our sun, a clock ticking 1 second would appear to a distant observer. Then, as the distance to the horizon shrinks towards 0 centuries, fall close enough, and from the outside, you would never actually appear to finish crossing the boundary at all. You would simply seem to freeze there, forever, growing dimmer and redder, an image of a person suspended at the edge of the universe's steepest hill. From your own perspective, falling, none of that freezing would be true. You would cross the horizon in an ordinary handful of seconds, feeling nothing unusual in the moment itself. No barrier, no wall, no sensation of crossing anything at all. Two accounts of the same event, both correct, both measured in principle, and utterly irreconcilable with each other. Before 1967, physicists had a different name for these objects, one that came directly from this frozen image. They called them frozen stars. Not because the star inside had stopped burning, but because that was exactly what a distant observer would see. A collapse that appeared to slow, stretch, and hang forever at the threshold, never quite finishing. The name black hole replaced it only because a physicist named John Wheeler needed something shorter for a conference talk. The older name, in some ways, described the outside view more honestly. That disagreement is not a flaw in the mathematics. It is the mathematics working exactly as Einstein's equations predicted in 1915, more than a century before any instrument existed, sensitive enough to confirm even the gentlest version of it in a laboratory down the hall. Two true stories, told from two positions in the same spacetime, neither one lying. So the forward direction is settled, layer by layer, height changes it, speed changes it, mass changes it enough to stop it entirely from someone else's point of view. While it keeps moving normally from your own, you are, in some small, measurable way, already a time traveler, and you always have been, every single day of your life. One heartbeat drifting very slightly out of step with the next, one floor of your body aging faster than another, one version of you racing ahead while the rest quietly follows. But gravity is only half of this story. There is a second lever bending time, one that has nothing to do with mass or height at all, and it's been sitting inside a fact you already heard. In the very first minutes of tonight, without anyone explaining why it's actually true. Go back to those muons for a moment, the ones raining down from the upper atmosphere that you heard about earlier, the ones that shouldn't reach the ground at all. Their secret has nothing to do with gravity. It has everything to do with how fast they're moving. A muon is created roughly 15 kilometers above your head, born when cosmic rays slam into the atmosphere with tremendous force. Left alone, a muon lives for about 2.2 microseconds before it decays into something else entirely. A lifespan so brief that even moving at nearly the speed of light, simple arithmetic says it should cover something like 600 meters before it disappears. 15 kilometers is 25 times farther than that. By every ordinary calculation, almost none of them should survive the trip down. Physicists first caught this directly in 1941 on the summit of Mount Washington in New Hampshire, comparing the number of muons detected at the peak to the number that survived the additional trip down to sea level. Bruno Rossi and David Hall found far more muons reaching sea level than ordinary, undilated decay rates could ever explain. One of the earliest direct experimental confirmations that Einstein's 1905 equations weren't just elegant mathematics on a chalkboard, but a description of something a Geiger counter could actually register, decades before satellites or atomic clocks existed to prove it any other way. Billions do anyway, and the answer isn't luck, it's speed itself, bending the muon's own private clock. Moving at 98% of the speed of light, a muon's internal stopwatch runs so much slower, relative to you standing on the ground, that its ordinary 2.2 microsecond lifetime stretches out to cover the entire descent. From your perspective, its clock is crawling. From its own perspective, if a muon could have one, nothing strange is happening at all. It lives its usual, unremarkable 2.2 microseconds. The 15 kilometers simply happens to fit inside that instant, because at that speed, the distance itself compresses to meet it. Two completely different explanations, both mathematically correct, both describing the same shower of particles. Time stretches for the moving thing, or space shrinks around it. Pick whichever description you prefer. And the muon still lands on your rooftop, having done something that, by any ordinary accounting, should have been physically impossible. Trillions of them pass through your body every single day. Right now, each one carrying its own tiny, perfectly consistent proof that the universe does not measure distance and duration the same way twice. This is the part almost nobody ever puts together. Even people who already know the muon fact by heart Gravity and speed are not the same trick, wearing two different masks. They are two entirely separate levers on the same machine, and they don't always pull in the same direction. Put two identical twins in motion relative to each other, and something in that same arithmetic stops staying simple at all. Two twins. Picture them as vividly as you can, because the rest of this only lands if they feel real. One stays exactly where he was born. The other boards a ship built to travel at 99% of the speed of light, bound for a star system a little over 8 light-years away, with orders to turn around the moment he arrives and come straight home. From the ground, the math is almost unbearable to picture. At that speed, the round trip takes a little over 16 years, measured by the calendars and birthdays of everyone who stayed behind. The traveling twin's own calendar tells an entirely different story. Because of exactly the same stretching that let those muons survive their fall, his onboard clock, his own heartbeat, his own aging, his own sense of an ordinary passing afternoon, runs dramatically slower than the one ticking on Earth. He steps off the ship having lived through roughly 2 1/3 years of ship time by his own calendar, his own memory, his own body. His twin, the one who never left, has lived through the full 16. Picture the reunion itself, because this is the part that stops being an equation and starts being a body standing on a landing platform. One brother walks down the ramp, still young, still exactly the way his sibling remembers him from the morning of departure. The other has spent over a decade building a life without him. Married, perhaps, with children old enough to ask why their uncle looks like their older brother's photograph. Same birth certificate, same parents, no longer remotely the same age. Nothing about the traveling twin's body did anything strange from his own point of view. He never felt himself slow down. He drank coffee, read books, slept in ordinary 8-hour stretches, exactly the way anyone does on any ordinary trip. From inside the ship, everything about his own life proceeded at its usual, unhurried pace. It was Earth that seemed to race ahead without him, 16 years compressed, from his vantage point, into a journey he experienced as barely more than 2. Mission planners, studying real interstellar concepts, already build this exact asymmetry into their projections. Breakthrough Starshot's proposed light sail probes, for instance, are designed to reach roughly 20% of light speed rather than 99%, and at only a fifth of light speed, the effect shrinks to something close to negligible. Push a crewed mission fast enough to make the effect matter within a human lifespan, and you are, by definition, also designing a mission that guarantees whoever climbs aboard will outlive everyone they leave behind on the ground. Both versions of the story are true at once, recorded on 2 different sets of instruments, and neither twin was lying, mistaken, or somehow cheating. Physics, which leaves exactly one uncomfortable question hanging over the whole scenario. If motion is only ever relative, if the traveling twin could just as easily insist that Earth was the thing moving away from him, then whose clock actually had the right to fall behind? Whose clock had the right to fall behind? It's a fair question, and for years after Einstein first published special relativity in 1905, it genuinely confused physicists who understood the mathematics perfectly well. If motion only means anything relative to something else, the traveling twin should be able to claim, with equal validity, that he stayed still, and the Earth twin was the one racing away at 99% of the speed of light. By that logic, it should be the Earth twin who ages more slowly. Both twins can't be right about who aged less. Someone has to actually be younger when the ship lands. The resolution has nothing to do with speed itself, and everything to do with the one thing that isn't symmetrical in this story. Only the traveling twin ever changes direction. Turning the ship around at the far star requires deceleration, a full stop, and acceleration back toward home. A break in an otherwise steady journey that the Earth twin never experiences at all. He simply stays in one uninterrupted frame of reference for the entire 16 years. The traveler does not. That single asymmetry, the moment of turning around, is what breaks the tie. It's the mathematical fingerprint that lets the equations say, without contradiction, which twin actually aged less. And it's the one detail most retellings of this story leave out entirely. None of this makes the age gap a trick of perspective. Something that would vanish if you looked at it correctly. Fly the ship, turn it around, fly it home, and the traveling twin lands on Earth with fewer birthday candles than his brother. Measured by every clock, every calendar, every strand of evidence anyone could examine. It has been tested directly, not with twins, but with atomic clocks flown on ordinary commercial jets, the same 1971 experiment you already heard about tonight. The two physicists behind it, Joseph Hafele and Richard Keating, spent a modest grant of about $8,000 buying commercial plane tickets for 4 cesium atomic clocks, seating them in their own row and flying them both eastward and westward around the entire planet. The numbers came back exactly as the equations predicted. To the microsecond. What's genuinely strange is how thoroughly this breaks an assumption most people never think to question. That everyone shares one universal gap of elapsed time between any two moments, the way everyone shares one universal ruler for measuring a room. They don't. Two people can leave the same room at the same instant and return to find they've lived through two different amounts of time, and both of them will be correct, and the disagreement will never resolve itself no matter how carefully anyone checks the math. If two people can disagree this completely about something as basic as how much time has passed, what happens to a system that depends on thousands of clocks scattered across the planet and orbiting above it, all needing to agree with each other every single second? Thousands of clocks, scattered across the planet and orbiting above it, all needing to agree with each other every single second. That system already exists. It's in your pocket right now. And it only works because engineers had to solve exactly this problem, using both kinds of time dilation you've already met, pulling in opposite directions at once. Every GPS satellite carries an atomic clock, orbiting at roughly 14,000 kilometers per hour, about 20,000 kilometers above the ground. Its speed alone, the same effect that let those muons survive their fall, the same effect that left the traveling twin younger, slows the satellite's clock down by about 7 microseconds every day relative to a clock sitting still on Earth. But the satellite is also much farther from Earth's gravity than you are, and weaker gravity, as you already learned watching a clock rise just 33 centimeters in a lab, makes time run faster, not slower. That altitude effect adds back about 45 microseconds a day. Subtract the smaller number from the larger one, and the satellite's clock ends up running about 38 microseconds ahead of clocks on the ground every single day, without fail, whether anyone on the ground is paying attention or not. Precisely the number you heard in the opening minutes of tonight's episode, explained now for what it actually is. 2 separate corrections, engineered into a system billions of people rely on without ever knowing it's there. 38 microseconds sounds negligible. It isn't. Left uncorrected, that drift would make GPS positioning accumulate an error of about 10 kilometers every single day. A satellite navigation system that starts out placing you in the right city, and within a single week ends up placing you somewhere in an entirely different neighboring country. Engineers solved this decades before most phones existed, building the correction directly into each satellite's onboard clock, tuning it to run intentionally slower before launch, so that once it reached orbit and sped up from both effects combined, it would land exactly on the correct rate. The adjustment is absurdly small on paper and enormous in consequence. Each satellite's onboard oscillator is built to tick very slightly slower than its natural rate of 10.23 MHz. The correction buried 9 decimal places deep. Invisible unless you already knew exactly where to look for it. A deliberate mistuning applied before the satellite ever leaves the ground specifically so that once gravity and velocity finish arguing with each other in orbit, the result lands on exactly the frequency engineers need. So, now, you have the full picture of the forward direction. Gravity bending it one way, speed bending it another. Engineers quietly accounting for both every time your phone finds your location on a map. Forward was always going to be solvable. It's the only direction time offers for free. The question this raises is far less comfortable. If forward can be engineered this precisely, down to a fraction of a millionth of a second, why has nobody, in over a century of trying, ever engineered a single microsecond going the other way? Nobody has engineered even a microsecond going backward, but one man has already traveled measurably further into the future than anyone else who has ever lived, without a single headline ever calling him a time traveler. His name is Sergei Krikalev, a Russian cosmonaut who spent a combined total of 803 days in orbit, across 6 separate missions, most of them aboard the Mir space station and the International Space Station, orbiting at speeds where the velocity effect, the same one that slowed the travelling twin, wins out over the weaker gravitational effect at low orbit. Net result: astronauts on the ISS age very slightly slower than everyone they leave on the ground, not faster. The opposite of what happens 20,000 kilometers higher aboard a GPS satellite. Add up all 803 days, and Krikalev returned to Earth having travelled about 0.02 seconds into his own future, arriving, in effect, 20 milliseconds ahead of where an ordinary, ground-bound version of his life would have placed him. Guinness World Records has recognised him, somewhat dryly, as the person who has spent the most time travelling forward relative to everyone he knows. It is, technically, an actual world record, sitting quietly next to categories for the largest pizza ever baked and the longest fingernails ever grown. 20 milliseconds is nothing you could ever notice. Blink, and you've lost more time than that to the blink itself. But it is real, measured, and stacked on top of a career that already included living through the collapse of the country that launched him. Krikalev left for one mission aboard Mir as a citizen of the Soviet Union in May of 1991, and returned the following spring to a nation that no longer existed by that name, his hometown now belonging to a different country entirely. He is sometimes called, informally, the last citizen of the USSR, having spent its final months quite literally above it, orbiting a place that changed its name while he wasn't looking. His return flight nearly became a diplomatic problem in its own right. The launch site at Baikonur, once simply Soviet territory, now belonged to the newly independent nation of Kazakhstan. And for a while, nobody was entirely certain which government was responsible for bringing him down. He eventually did land on a step that technically wasn't part of the same country he'd left from, having orbited the planet more than 5,000 times without it ever occurring to the planet, apparently, to just stay still and wait for him. Time moved forward for him twice, in 2 completely different senses, within the same handful of months. 20 milliseconds one way, measured by physics, an entire country. Gone, measured by history. Only one of those was ever going to show up on a clock, but both kinds of arrival share the same unsettling shape. Gone, and returned to find that the word now no longer quite pointed at the same thing it used to. No longer quite pointed at the same thing it used to. That phrase turns out to be truer and stranger than anyone intends it to be when they say it about a place they've been away from. In Relativity, now was never a single, agreed-upon instant shared by the whole universe. It only feels that way because everything in ordinary daily life moves too slowly for the disagreement to matter. Here's the actual claim, and it belongs among the strangest sentences physics has ever forced anyone to take seriously. 2 events can happen at exactly the same time for one observer and at measurably different times for another observer watching the same 2 events, with neither observer being wrong, not a trick of light delay, the ordinary kind you already understand. The fact that a lightning flash reaches your eyes before its thunder reaches your ears. This runs deeper than that. Even after every delay from the finite speed of light gets carefully subtracted out, the actual order of two events, which one happened first, can flip depending entirely on how fast you happen to be moving relative to them. Anchor it in something almost every physics classroom uses. Two lightning bolts strike a long, moving train at its front and back. At what a person, standing on the platform, measures as the exact same instant. To that platform, observer, simultaneous, no argument. But a passenger sitting in the middle of the train, moving toward the front strike and away from the back one, receives the front flash's light slightly sooner than the back flash's light, and after accounting for every bit of travel time correctly, still concludes with full mathematical justification that the front strike happened first. Not an illusion caused by the delay, a genuine, physically real disagreement about the order of two events built into the geometry of spacetime itself, with nobody making any mistake at all. Now put yourself in the passenger's seat. In the most literal sense the universe allows, every time you walk briskly across a room, you shift by an amount so vanishingly small it would take instruments far more sensitive than anything in an ordinary lab to catch it. Which distant events count as happening now for you, compared to someone sitting still a few feet away? You have never once shared a perfectly identical now with another moving person in your entire life. You've only ever been close enough that the difference didn't matter. It starts to matter enormously once distance gets involved. Walk toward a wall at an ordinary strolling pace, and the now slice of the universe that includes you, extended outward across billions of light years in the direction you're walking, tilts forward in time by an amount that would be genuinely significant on a galactic scale. Years, not microseconds, once the distance is large enough. Physicists have a name for exactly how far that mismatch can stretch, and it involves a galaxy you can already see with your own naked eye on any clear night. A galaxy you can already see with your own naked eye on any clear night. Andromeda sits about 2.5 million light-years away, close enough to spot as a faint smudge without a telescope, far enough that the mismatch in now you just learned about stops being a rounding error and becomes something physicists take seriously enough to name. Physicist Roger Penrose worked out the actual numbers decades ago, and the result is now known as the Andromeda paradox. Picture two people passing each other on a sidewalk, walking in opposite directions at an ordinary strolling pace. Nothing dramatic, nothing close to relativistic speed. According to the relativity of simultaneity, the slice of the universe each of them would currently call right now on Andromeda differs by several days, simply because of the tiny difference in their walking velocities. One pedestrian's present moment, extended out across 2.5 million light-years, includes events on Andromeda that the other pedestrian's present moment has not reached yet, or has already left behind. Neither pedestrian would ever notice, of course. The disagreement lives entirely in a galaxy neither of them will visit, involving a now they'll never be able to check against anything. But the mathematics behind it is exactly the same mathematics that keeps a GPS satellite accurate to the meter. The same mathematics confirmed to the microsecond by clocks flown around the planet in 1971. It doesn't switch off at extreme distances. It simply becomes visible there in a way it never can at the distance between two people on a sidewalk. Turn around and walk the other direction instead, and the disagreement flips. Whatever event on Andromeda used to belong to your future now belongs to your past, or the reverse, decided entirely by which way you happened to be facing when you tied your shoes that morning. Nothing about Andromeda itself changed in either scenario, only the direction of an ordinary walk on Earth. This is the detail that makes physicists uneasy in a way that gravitational time dilation, oddly, never quite managed to. Gravity and speed change how fast your clock ticks, but they still leave you with one continuous, orderly, personal timeline. Your own private river, running at its own private speed, but a river nonetheless. The relativity of simultaneity does something stranger. It suggests that now was never a single moving line sweeping across the universe, agreed on by everyone, arriving at each event in the same order. It suggests instead that every possible now, for every possible observer, already exists, laid out all at once, like pages of a book that has already been written, waiting only for a particular reader's particular pace to determine which page a given walk happens to fall open to. Physicists have a formal name for that idea, and it forces an uncomfortable question about the difference between your past, which everyone agrees is fixed and unchangeable, and your future, which everyone agrees is still open and undecided. If both of those already exist on the same page, laid out together in the same already written book, what exactly is the difference between them supposed to be? What exactly is the difference between them supposed to be? Take the relativity of simultaneity seriously enough. Follow its logic all the way through, and a specific, unsettling picture falls out of the mathematics almost on its own. Physicists call it the block universe, or eternalism, when they want to be precise about it. The idea that past, present, and future are not three different categories of existence, with the past gone, the future not yet real, and only the present actually happening. Instead, all three are equally real, equally fixed, equally there, laid out together across 4 dimensions the way a landscape is laid out across 3, with your sense of a moving now being something closer to a spotlight sweeping across an already existing terrain than an actual boundary between what exists and what doesn't. Under this view, your 5th birthday party didn't stop existing when it ended. It's still there. In the same sense, a city you've already driven through is still there, behind you on the map, even though you're no longer looking at it. Your death, whenever and however it happens, already exists too, in exactly that same sense. Not as a prediction, not as a probability, but as a fixed point on the same unchanging landscape as everything else. Nothing about the block universe requires anything to be predetermined by fate or by some outside will. It only requires that the mathematics of relativity, which nobody seriously disputes, be taken at its word about what now actually means. Not every physicist accepts this picture, and the ones who resist it tend to resist it for a specific reason. It seems to erase the difference between something that already happened and something that hasn't happened yet. A difference that feels, to nearly every human being who has ever lived, like the most obvious fact about reality there is. Alternative interpretations exist, the growing block model, where the past is fixed but the future is genuinely not yet real, added to the block moment by moment, like new pages appended to a book that isn't finished. No experiment has ever managed to tell these interpretations apart. The equations of relativity work exactly the same either way. The disagreement, for now, belongs to philosophy exactly as much as it belongs to physics, and no instrument yet built has ever managed to settle it either way. Here's what nearly everyone on both sides of that argument does agree on, though, and it's the detail that actually matters for tonight. Nothing in Einstein's equations forbids information, or a person, or an object from existing at more than one point along that fixed landscape in a way that violates the ordinary, one-directional order everyone experiences by default. The mathematics that lets 2 pedestrians disagree about Andromeda's present moment is built from the exact same geometry that some physicists believe, in principle, permits a much stranger kind of disagreement. One where a person's future and a person's past could, under sufficiently extreme conditions, actually reach out and touch. Einstein and a colleague named Nathan Rosen worked out exactly how, in 1935, while trying to solve a completely different problem. They were looking for a way to describe fundamental particles using pure geometry, without needing to treat them as points of infinite density. And one of the byproducts of that search was a mathematical structure now called the Einstein-Rosen bridge. Better known today by the name a physicist named John Wheeler gave it decades later: a wormhole. An Austrian physicist named Ludwig Flamm had actually noticed the same geometric structure buried inside Karl Schwarzschild's original 1916 solution for a black hole nearly 2 decades before Einstein and Rosen wrote their own paper. But Flamm's version went almost entirely unnoticed at the time, filed away in a journal nobody outside a small circle ever read closely. The geometry is strange enough to describe carefully. Picture spacetime not as a flat surface, but as something that can fold, the way a sheet of paper folds. Draw 2 distant points on that paper, one representing your solar system and one representing a location on the far side of the observable universe. On the flat, unfolded sheet, reaching the second point means crossing every inch of paper in between. The ordinary way you'd normally assume distance has to work. Fold the paper instead and bring the 2 points close enough to touch through the fold, and a hole punched straight through connects them directly, with a tunnel far shorter than the distance either point would measure across the folded surface. Einstein's equations don't just permit a fold like that. In their purest mathematical form, they practically expect one. Here's the part that separates this from the science fiction version almost everyone already has in their head. Not a single wormhole has ever been detected anywhere, at any scale, in over a century of looking. The equations describing them are completely legal. The astrophysical evidence that any of them actually exist anywhere in the observable universe is exactly 0. Not rare, not merely unconfirmed, but entirely absent from every survey astronomers have ever run. And even in the mathematics, the original 1935 version comes with a serious problem attached. The tunnel it describes is unstable, closing itself off in less time than it would take even a beam of light to cross from one end to the other. On paper, in its rawest form, a wormhole built this way collapses before anything could ever use it. A door that opens and slams shut again faster than even light could get a foot through it. Which raises the obvious question honestly. The one most retellings skip entirely in favour of the exciting part. If the simplest version of a wormhole seals itself shut instantly, faster than anything could ever cross it, what would it actually take, physically, to prop one open long enough for something? Light, information, you yourself, to make it all the way through to the other side? What it would actually take to prop one open long enough for something to make it through. Picture, for a moment, that the engineering problem has already been solved. Set aside how, just for now, and a stable, traversable wormhole floats in open space in front of you, its mouth roughly the width of a doorway, rimmed with a faint, distorted halo where the light from behind it bends sharply around the opening's edge. Unlike the black hole you already stood at the edge of earlier tonight, nothing about approaching this doorway would tear you apart. A black hole's tidal forces come from gravity increasing sharply over a very short distance, stretching anything crossing the horizon into something closer to a thread than a body. A wormhole, if one could actually be built and held open, wouldn't need to work that way at all. The entire appeal of the design, to the physicists who study it seriously, is a tunnel gentle enough for an ordinary human body to walk through without injury. The same way you'd walk through any other doorway, from just outside it, looking in, you would see something genuinely disorienting. Not darkness, the way a black hole shows you, but an image, a distant nebula, a different sky, possibly a different galaxy entirely, depending on where the far mouth had been placed, folded impossibly close and visible through an opening you could reach out and touch, step through, and by every account the mathematics allows, the crossing itself would feel unremarkable. No falling sensation, no stretching, nothing that resembled crossing any real distance at all, because from the inside, almost none actually would be. One step, and the sky behind you would already belong to somewhere else. This is precisely why serious physicists take the idea seriously enough to keep working on it, decades after Einstein and Rosen first sketched the geometry. Unlike faster-than-light travel through ordinary space, which relativity forbids outright and without exception, a wormhole doesn't ask anything to move faster than light at all. It only asks space itself to be folded in a way that makes an enormous distance geometrically short. Nothing inside the tunnel would need to break a single one of Einstein's rules to make the trip in what felt, to the traveler, like a single ordinary step. This same picture, worked out rigorously rather than imagined loosely, is exactly what physicist Kip Thorne handed to the visual effects team behind the 2014 film Interstellar. Real general relativity equations, solved and rendered frame by frame, producing an image close enough to physically accurate that Thorne later published the resulting calculations in an actual peer-reviewed astrophysics journal. Nothing about that ease is free, though the universe, so far, has never once been observed handing out a shortcut this generous without demanding something extraordinarily difficult in return. And the price tag on this particular shortcut turns out to be one of the strangest ingredients physics has ever proposed needing on purpose. One of the strangest ingredients physics has ever proposed needing on purpose. In 1988, physicists Michael Morris and Kip Thorne worked out exactly what it would take to keep a wormhole open long enough to actually use, not as speculation, but as a serious paper published in a serious physics journal, reverse engineering the geometry of a perfectly stable tunnel from scratch, and then asking, rigorously, what kind of matter, if any, could physically hold that geometry open. The answer they found is almost defiantly strange. A traversable wormhole needs exotic matter, a substance with negative energy density, meaning it would need to gravitationally push outward instead of pulling inward, behaving, in effect, like anti-gravity, holding the throat of the tunnel open against its own natural tendency to collapse shut. Ordinary matter, no matter how much of it you gathered or how you arranged it, only ever pulls. Every planet, every star, every human body obeys that rule without exception. What Morris and Thorne's mathematics demanded instead was something nothing in nature had ever been caught doing. Pushing rather than pulling. Anywhere, at any scale, in any laboratory, on any world. It isn't entirely fictional though, and this is the detail that keeps the idea from being dismissed outright. In 1948, physicist Hendrik Casimir predicted, and later experiments confirmed, that two uncharged metal plates placed extremely close together in a vacuum would be pushed toward each other by a measurable force. The Casimir effect, caused by the plates restricting which quantum vacuum fluctuations can exist in the narrow gap between them, producing a tiny region of genuinely negative energy density relative to the vacuum outside. The effect is real, repeatedly measured in laboratories, and undeniably an example of exactly the kind of exotic energy a wormhole would need. The gap between that laboratory measurement and what a wormhole would actually require, though, is almost impossible to overstate. The negative energy produced between two Casimir plates is astronomically smaller than what Morris and Thorne's equations call for. By some estimates, sustaining a wormhole large enough for a person to walk through would require a region of negative energy roughly equivalent to the total energy output of an entire galaxy, concentrated and maintained indefinitely. Using physics that has only ever been observed at scales too small to see without specialized equipment, in quantities that wouldn't cover a single dust particle, let alone a doorway a human being could actually walk through and out the other side. So, the door isn't closed. Nothing in the mathematics forbids exotic matter from existing in the necessary quantities. It simply hasn't been found anywhere in anything close to a useful amount, which leaves the wormhole exactly where it has sat since 1935. Legal, on paper, drawn out in complete mathematical detail, and entirely out of reach for reasons that have nothing to do with imagination and everything to do with a universe that has never yet handed anyone that particular ingredient in any usable quantity. Entirely out of reach for reasons that have nothing to do with imagination. But suppose, just for the sake of the mathematics, that the exotic matter problem eventually gets solved. Enough negative energy gathered and held in place, keeping a wormhole open indefinitely. Kip Thorne noticed something else buried in the same equations, a consequence so strange that even he described it, in his own writing, as something he almost didn't believe at first when a graduate student pointed it out to him. A stable, traversable wormhole wouldn't just connect two distant places. Under the right conditions, it would connect two entirely different times. Here's how the trick works. In principle, take one mouth of the wormhole and leave it exactly where it is. Take the other mouth and accelerate it to a significant fraction of the speed of light. Send it on a long journey and bring it back, using precisely the same time dilation you already learned about earlier tonight. The same effect that left the traveling twin younger than the one who stayed home. The traveled mouth ages less than the stationary one. Reconnect them, and the wormhole now links two ends that disagree about what time it currently is. One mouth still living in an earlier moment, relative to the other, by exactly the same gap the twins would have accumulated. Step through the stationary mouth going in, and you emerge from the traveled mouth, arriving in the past, relative to where you started, by an amount equal to the accumulated time difference between the two ends. Reverse direction, entering through the traveled mouth instead, and you travel forward in time relative to your starting point. The wormhole itself never breaks a single rule of relativity to make this happen. It only exploits the fact that its two mouths, having taken different paths through space-time, no longer agree on the current date. A disagreement that would already exist between any two clocks, separated the exact same way, wormhole present or not, patiently, in the background, the entire time. There's a hard limit built into the trick, though. One that keeps it from being quite as generous as it first sounds. The time machine only starts working from the moment the two mouths' clocks begin to diverge. The instant the travelling mouth first sets off, nobody could use a wormhole built this year to visit any date earlier than this year. Not the fall of Rome, not the age of the dinosaurs, not even last century. The tunnel doesn't offer access to the deep past, the way fiction often imagines it. It only offers a narrow window stretching from the moment of its own construction onward. Growing wider, the longer the wormhole exists, and the more its two ends continue to disagree about the date. Still, a narrow window is not the same thing as no window at all. And once even that much became mathematically legal, physicists went looking for exactly how far the legality actually extended. In 1949, a mathematician named Kurt Gödel handed Albert Einstein an unusual gift for his 70th birthday. Not an object, but a solution to Einstein's own field equations, one Einstein had never considered on his own and, by most accounts from colleagues who were there, found genuinely disturbing once he saw it laid out in full. Gödel and Einstein were close friends by then, long-time walking companions at the Institute for Advanced Study in Princeton, where colleagues sometimes joked that Einstein's own office existed mainly so he'd have somewhere to keep his coat before the two of them left for their daily walk together. Gödel, more famous by that point for his incompleteness theorems in mathematical logic than for physics, had taken up general relativity almost as a side project, working through Einstein's equations with the same exacting rigor he brought to everything else. What he found was a specific, mathematically valid solution describing a universe that rotates as a whole, not around any external point, since there would be nothing outside it to rotate around, but rotating in the sense that every object within it experiences a kind of large-scale cosmic swirl. In a rotating universe of that kind, Gödel showed The geometry of spacetime bends enough that certain paths loop back on themselves entirely. A traveler, following one of these paths, a closed time-like curve, in the formal language physicists still use for it, could travel far enough along their own future and arrive back at their own past, meeting an earlier version of themselves without ever reversing direction, without breaking a single local law of physics along the way. Picture yourself as that traveler for a moment. Every step you took would feel like ordinary forward motion, right up until the horizon ahead of you turned out to be the place you'd already started. Every step of the journey would feel, to the traveler, the loop would only become apparent from the outside, or after arriving somewhere that turned out to already be where the traveler started. Our own universe, as far as every observation to date has shown, is not rotating in the way Gödel's solution requires. The real universe appears to be expanding, not spinning, and no closed time-like curve has ever been found in it. Gödel never claimed otherwise. His point was narrower and, in its own way, more unsettling. He had shown that Einstein's own equations, the same equations underlying everything from GPS satellites to gravitational time dilation, permitted time travel into the past as a matter of pure mathematical consistency in at least one legitimate solution. Not a flaw in the theory, a feature of it, sitting quietly inside the mathematics the entire time, waiting for someone patient enough to go looking. Einstein's own response, recorded by colleagues who knew him at the time, was measured but unmistakably uneasy. He acknowledged the solution was valid, while writing that it would be interesting to know whether such things could be excluded on physical grounds. Decades later, physicists are still trying to answer exactly that question, and the closest thing to an answer has never once been a simple no. The closest thing to an answer has never once been a simple no. The objection almost everyone raises first. The moment backward time travel gets taken seriously, even as a hypothetical, has a name: the grandfather paradox. Travel into the past, the argument goes, and prevent your own grandfather from ever meeting your grandmother. If he never meets her, your parent is never born. If your parent is never born, neither are you. And if you were never born, you couldn't have traveled into the past to prevent the meeting in the first place. Which means your grandfather does meet your grandmother after all. Which means you are born. Which means you can travel back and prevent it. Which means he doesn't. The logic doesn't resolve cleanly in either direction. It only loops, endlessly, refusing to settle on a single, consistent version of events. Strip away the family drama, and the actual problem underneath has nothing specifically to do with grandparents at all. It's a problem about self-consistency. Can a closed time-like curve, the kind Gödel's mathematics allows, contain an action that erases the very condition that made the action possible? Physicists studying this seriously don't ask whether time travel is emotionally troubling, or whether it would be wise, or whether anyone would even want to attempt it. They ask something narrower and far more answerable: whether the equations describing a closed time-like curve can be solved at all once an event inside that loop tries to contradict its own cause. Two broad answers have emerged from decades of taking the question seriously as mathematics rather than as family melodrama. The first, associated most closely with physicist Igor Novikov, argues that the universe simply wouldn't permit the contradictory version of events to occur, not through any conscious intervention, but because the laws of physics themselves would only ever allow self-consistent solutions along a closed time-like curve. On this view, if you traveled back intending to prevent your grandparents from meeting, something would always, without fail, prevent your interference from succeeding. Not fate, not destiny, just the ordinary requirement that a mathematically consistent solution has to exist. The same requirement that already governs every other equation in physics. The second answer takes a different escape route entirely, borrowing from an idea already familiar from quantum mechanics: that traveling into the past doesn't alter your own timeline at all. but instead branches off an entirely separate one, a parallel version of history where your intervention succeeds while your original timeline continues, untouched, exactly as it always had. Your grandfather still meets your grandmother in the timeline you left behind. You simply no longer belong to it. Neither answer has ever been tested, because a closed time-like curve of any kind remains something no laboratory has ever managed to build. Both remain exactly what they've been since the question was first taken seriously. Decades ago now. Fully consistent, fully unconfirmed, and entirely dependent on a piece of engineering nobody currently has any real path toward building. Fully consistent, fully unconfirmed, and entirely dependent on a piece of engineering nobody currently has any real path toward building. But imagine, for a moment, that the engineering existed anyway, and picture yourself watching from just outside the loop as a working closed time-like curve opens, and a person steps toward the edge of it, intending to test the Novikov self-consistency principle directly, on purpose, with full knowledge of what she's attempting. She steps through carrying a single loaded rifle, with a plan simple enough to state in one sentence. Travel back exactly 1 hour, find her earlier self standing in this same room, and fire, ending the loop before it can complete itself. She arrives on schedule. Her earlier self is exactly where the plan predicted. Facing away, unaware, she raises the rifle, aims carefully, and pulls the trigger. The gun jams. Not dramatically, no sparks, no explanation, just an ordinary, mundane mechanical failure of the kind that happens to firearms sometimes for entirely unremarkable reasons that have nothing to do with time travel at all. By the time she clears the jam, her earlier self has turned around, startled by the noise, and the moment for a clean shot has already passed. She tries again a second later. Her foot catches on a cable she hadn't noticed, and the shot goes wide. A third attempt ends when her earlier self, now alarmed, simply grabs her arm. A fourth attempt never happens at all. By then, the room is too crowded with two versions of the same panicked person, grappling, shouting over each other in the same voice. And the rifle ends up on the floor between them, forgotten before either one quite decides how it got there. Nothing about any single obstacle looks engineered. A jammed gun, a stray cable, a moment of quick reflexes. Any one of them, taken alone, is the kind of ordinary bad luck that happens to people every day, time travel or not. Taken together, forming a perfect unbroken wall around one specific outcome, they start to look like something else entirely. Not chance, but a boundary the mathematics itself seems to be quietly enforcing from somewhere outside the room. This is the Novikov principle rendered as a scene instead of an equation, and it's worth sitting with the specific discomfort it produces rather than resolving it too quickly. The self-consistency principle doesn't promise a universe that protects itself dramatically with lightning and warning signs. It promises a universe that protects itself boringly through an unbroken sequence of small, forgettable failures that never individually look like anything and never once feel, from the inside, like fate. We still don't actually know whether this is what a real closed time-like curve would do, or whether it would feel this mundane, this physical, this stripped of anything resembling drama if you were ever the one standing close enough to watch it happen. Nobody has ever stood in that room, and tonight, that's exactly where we'll leave her. Rifle on the floor, two versions of the same person still catching their breath, the loop closing itself quietly. The way the mathematics says it always would. The loop closing itself quietly, the way the mathematics says it always would. That's a scene. Physicists wanted something closer to an actual calculation. And in the early 1990s, a small group of them, including Igor Novikov himself, working with physicist Fernando Echeverria and mathematician Gunnar Klinkhammer, found a way to test the self-consistency principle using one of the simplest physical systems imaginable. A billiard ball a wormhole small enough for the ball to pass through, and pure classical mechanics. The setup. A billiard ball is launched toward a wormhole mouth at a carefully chosen angle. The wormhole is arranged so that the ball emerges from the other mouth slightly earlier than it entered. A miniature version of exactly the time machine trick Thorne had already worked out, on a trajectory that would, if nothing intervened, send the earlier version of the ball colliding with its own later self, knocking it off course before it ever reaches the wormhole mouth at all. On paper, this looks like the grandfather paradox reduced to the simplest object physicists could think to use. Novikov, Echeverria, and Klinkhammer ran the actual equations of motion, checking whether any physically consistent solution could be found. It could. In fact, the mathematics turned up an entire family of solutions in which the earlier ball delivers a glancing blow rather than a dead-on collision, nudging its later self just enough to alter its path slightly, in exactly the way needed for it to still enter the wormhole, still travel back, and still deliver that same glancing blow, closing the loop perfectly instead of preventing it. No contradiction, no paradox, just ordinary billiard ball physics, quietly finding its own way to stay consistent, the same way water finds its way downhill without needing to be told which route to take. There's something almost comic about the image, and it's worth letting the comedy sit for a moment rather than rushing past it, the way you might pause on a joke that turns out to be smarter than it first sounded. The grandfather paradox, one of the most famous thought experiments in the history of physics, reduced by serious researchers to a pool table, a wormhole the size of a coin, and a ball nudging itself just hard enough to save its own future without erasing it. Nobody solved the deep philosophical question this way. What they showed, rigorously, was narrower and in some ways more reassuring. Nothing in classical mechanics forbids a self-consistent solution from existing, even in a system deliberately built to create a paradox. The universe, at least on a billiard table, always seemed to find a way to avoid contradicting itself, quietly, without needing anyone to intervene. Whether a real, closed, time-like curve, built from space-time instead of felt and slate, would behave with the same billiard ball patience remains completely unknown. The experiment has never been scaled up. Nobody currently has a wormhole small enough to try, or a table big enough to place it on, or a way to run the experiment anywhere outside a set of equations on a chalkboard, leaving you, for now, with nothing more solid than the calculation itself to trust. Nobody currently has a wormhole small enough to try. Physicist J. Richard Gott looked for an entirely different route to the same destination in 1991. One that didn't require exotic matter, wormholes, or a rotating universe at all. Only an object cosmologists already suspected might genuinely exist. The cosmic string. Cosmic strings, if they exist, would be leftover defects from the early universe, formed in the first fractions of a second after the Big Bang, the way cracks form in ice as it freezes too quickly. Incomprehensibly thin, narrower than a proton in some models, but carrying an enormous concentration of mass along their length, dense enough to warp space-time measurably around them despite their vanishing width. Gott's calculations showed that two cosmic strings, passing each other at a sufficiently high fraction of the speed of light, would warp the space-time between them so severely that a closed time-like curve would open up in the region where their gravitational effects overlapped. A genuine, mathematically legitimate time machine built entirely from geometry. One that, in principle, wouldn't need you to find any exotic matter at all, or wait for a rotating universe you don't actually live in. The catch arrived almost immediately, and it's a serious one. To actually create the effect, the two cosmic strings would need to pass each other at a speed corresponding to an energy density so extreme that, according to a separate calculation published soon after by other physicists, building the setup in the first place would require more energy than exists in the entire observable universe. Not more energy than humanity could generate, which would already be a serious problem, but more than every star, every galaxy, and every particle of dark matter combined could theoretically provide, even given unlimited time to gather it. Gott's mathematics was airtight, checked and rechecked by other physicists who found no error in it. Gott's mathematics was also, for all practical purposes, describing a machine no civilization, however advanced or however patient, could ever realistically gather enough energy to power on. No cosmic string has ever been directly detected either. Gravitational lensing surveys, designed specifically to catch the telltale signature these objects would leave in the light of background galaxies, have come back empty every time they've looked. They remain a theoretical prediction from certain models of the early universe, neither confirmed nor ruled out, sitting in the same category as so much else discussed tonight. Legal on paper, drawn out in complete mathematical detail, absent so far from every observation anyone has managed to make in decades of watching the sky specifically for them. What Gott's proposal did accomplish, regardless of whether cosmic strings turn out to be real, was widen the list of routes mathematics offers toward a closed time-like curve, rotating universes, wormholes stretched by relativistic travel, cosmic strings passing each other at extreme velocity, three completely different physical setups, discovered independently by three different researchers working decades apart, all arriving at the identical conclusion. Nothing in the equations of general relativity, taken on their own terms, forbids a loop in time from forming. The equations kept saying yes. It was a different branch of physics that finally stepped in to ask whether yes was actually the right answer to be giving. It was a different branch of physics that finally stepped in to ask whether yes was actually the right answer to be giving. In 1992, Stephen Hawking proposed exactly that challenge, in a paper with a title blunt enough to double as its own conclusion: the chronology protection conjecture. His argument wasn't that closed time-like curves were mathematically impossible. You already know better than that by now. Having watched Gödel, Thorne, and Gott each show otherwise, his argument was that something else in physics, something not yet fully accounted for in these classical calculations, would always intervene before a closed time-like curve could actually form. Hawking's specific mechanism involved quantum effects near the boundary of a would-be time machine. As a closed time-like curve gets close to forming, Hawking calculated vacuum fluctuations, the same background quantum activity responsible for the Casimir effect you already heard about, would circulate around the loop an effectively enormous number of times, building up to a runaway energy density right at the point where the loop would otherwise close. That energy build-up, he argued, would destroy the very structure that was about to create the time machine, an instant before it finished forming. Not a moral law, not a paradox resolving itself after the fact, a physical safety mechanism built into the quantum vacuum itself, quietly demolishing every time machine at the exact moment of completion. Hawking illustrated his own confidence in the idea with a genuinely famous demonstration. In 2009, he hosted a party, champagne, balloons, a banner, and sent out the invitations only after the party had already ended, publicizing the date and location for the first time the following day. The logic was playful but entirely serious underneath. If backward time travel is ever going to be possible at any point in humanity's future, someone from that future should have been able to receive an invitation sent after the fact and attend anyway. Nobody showed up. Hawking treated the empty room, with visible amusement, as very weak but genuinely real evidence in favor of his own conjecture. The chronology protection conjecture remains unproven, exactly like everything else discussed tonight in this stretch of the episode. Hawking himself was careful to describe it as a conjecture rather than a theorem, an educated guess about where an incomplete piece of physics, a full theory of quantum gravity that doesn't exist yet, would eventually land once someone finally works it out. That theory doesn't exist yet. No one can currently calculate, with full rigor, whether Hawking's vacuum fluctuation mechanism would actually behave the way his approximate calculations suggested, or whether some cleverer configuration might slip past it entirely. What Hawking's conjecture represents, more than a specific mechanism, is a pattern that keeps recurring throughout this entire investigation. Every time one branch of physics opens a door to the past, a different, less complete branch of physics shows up, suggesting the door might close itself before anything can walk through. Nobody has proven the door stays shut. Nobody has proven it stays open either. Nobody has proven it stays open either. There's one more route toward the past worth understanding, and it circles back directly to the strangest thing you learned earlier tonight about the word now. It doesn't require wormholes, rotating universes, or cosmic strings. It only requires something moving faster than light, which sounds like an entirely different problem from backward time travel, until the relativity of simultaneity gets involved. Remember the two pedestrians disagreeing about Andromeda's present moment, simply because of their different walking speeds. Push that same effect to its logical extreme, and something specific happens. For an observer moving fast enough, relative to a signal traveling faster than light, the order of cause and effect can flip entirely. A message sent faster than light, from your perspective, can arrive at its destination and be sent back faster than light again by the receiver, before you, the original sender, ever sent it in the first place. Physicists call the resulting thought experiment a tachyonic anti-telephone, a device that, if faster than light signaling were possible at all, could deliver a reply to a message before the message was ever sent, turning an ordinary conversation into a genuine paradox generator. This is precisely why relativity treats the light speed limit as absolute rather than merely impressive. It isn't primarily a speed limit in the way a highway sign is a speed limit, an arbitrary ceiling that happens to be enforced. It's a causality limit. Break it, even briefly, even with something as simple as a single signal, and the relativity of simultaneity. The same effect that makes now different for two ordinary pedestrians turns that single faster-than-light signal into a message capable of arriving in its own past. Cause and effect, the entire structure holding a coherent, sensible sequence of events together, would stop being guaranteed for anyone, anywhere, moving at any speed at all, replaced by a universe where the order of events depended entirely on who happened to be watching and from where. Nothing observed in over a century of experiments has ever shown anything crossing that boundary. Particles have been accelerated to a hair's breadth below light speed repeatedly in laboratories built for exactly that purpose. And every single one behaves exactly as relativity predicts, requiring more energy the closer it gets, and never quite arriving at the limit itself. The wall holds every single time anyone has ever tested it directly, in every laboratory that has ever tried, without a single documented exception in over 100 years of looking, which leaves backward time travel resting on a strange and consistent foundation once every route tonight gets laid side by side. Wormholes need matter that has never once turned up in bulk, anywhere. Cosmic strings need energy no civilization could gather. Rotating universes don't match the one we actually live in, and the light speed wall, the most heavily tested limit in the history of physics, has never once been breached, not by a single particle, not by a single microsecond, not by a single particle, not by a single microsecond. That hasn't stopped physicists from actually looking, seriously and specifically, for evidence that any of this has ever happened anyway. In 2013, astrophysicist Robert Nemiroff and a student ran an unusual search, combing social media and search engine records for any mention made before a major news event of specific and highly unlikely search terms connected to that event. Pope Francis's name before his selection, for instance, or Comet Ison's exact trajectory before it was announced, looking for anything that could only be explained by someone already knowing what was about to happen. The kind of trace you yourself might leave behind, without meaning to, if you ever slipped and mentioned tomorrow's headline a day early. They found nothing. Not one credible instance across the enormous volume of data available, of information appearing on record before the event that would have generated it. Nemirov was careful, and slightly wry, about the limits of the method. The search only covered a specific window of the internet, could easily miss a time traveler cautious enough to avoid mentioning anything checkable, and proved absence of evidence rather than anything stronger. Still, it stands as one of the more genuinely creative attempts anyone has made to test the question empirically, instead of just mathematically. A separate, more conventional search has been running for years at the Large Hadron Collider, where physicists have specifically examined particle collision data for a theoretical particle called a Higgs singlet, a hypothetical cousin of the Higgs boson that, according to some models involving extra dimensions, could behave in ways that let it briefly disappear from ordinary spacetime and reappear at an earlier point, exploiting a loophole in certain higher dimensional theories rather than violating relativity directly. No such signal has ever turned up in the data. The search continues each time the collider runs, quietly folded into experiments built primarily to look for other things entirely. A kind of standing background check, run automatically, on every single collision the machine produces, whether or not anyone is actively thinking about time travel that day. The theoretical case for even looking came from physicists Tom Weiler and Cui-Man Ho, who argued in 2011 that if extra spatial dimensions exist, a real, seriously debated possibility in several branches of modern physics, entirely separate from anything discussed so far tonight, a particle briefly slipping into one of those extra dimensions could reappear in ordinary spacetime at a point earlier than when it left, without technically violating relativity within our own 3 dimensions at all. It was a narrow, specific, falsifiable prediction. The collider looked. It found nothing. None of these searches expected to succeed, and none of the physicists running them were especially surprised when they didn't. What they represent instead is a specific kind of intellectual honesty running underneath this entire episode. A willingness to take a mathematically legal possibility seriously enough to actually go check using real instruments and real data, rather than dismissing it as fiction or accepting it as inevitability. Every check has come back the same way. Not proof that backward time travel is impossible, only silence, collected patiently, experiment after experiment, from a universe that has so far declined to answer the question either way. Only silence, collected patiently, experiment after experiment, from a universe that has so far declined to answer the question either way. One more proposal deserves a place in this account, because it doesn't fit neatly into either of the 2 answers already covered. Self-consistency on one side, branching timelines on the other. In 1991, physicist David Deutsch, one of the founding figures of quantum computing, proposed a third option, built not from general relativity, but from quantum mechanics itself. Deutsch's approach treats a closed time-like curve as a quantum system, subject to the same rules of superposition that already govern every particle physicists study in ordinary laboratories. In quantum mechanics, a particle doesn't have to be in one definite state before it's measured. It can exist in a superposition of multiple possible states simultaneously, with definite values only emerging at the moment of observation. Deutsch's insight was to apply that same logic to a time traveler stepping into a closed loop, rather than requiring the loop to settle on one single, self-consistent classical history, the way Novikov's approach demands, or splitting into 2 entirely separate branching universes, the way the many worlds approach demands. Deutsch's model allows the loop to exist in a quantum superposition of many slightly different, mutually consistent histories at once, weighted by probability, resolving only when something inside the loop is actually measured. Run the grandfather paradox through Deutsch's mathematics, and something genuinely strange falls out. A self-consistent solution always exists, but it isn't unique, and it isn't classical. The traveler who goes back with a gun doesn't definitely succeed or definitely fail in preventing their own birth. Instead, Quantum probability distributes itself across every version of events that remains internally consistent, in a way that has no equivalent anywhere in classical physics. Closer to the strange, probabilistic reality already known to govern electrons and photons than to anything from Newtonian intuition about billiard balls and gunshots. Deutsch's model has one advantage the others lack. It makes a testable prediction, at least in principle, using existing quantum computing techniques. Physicists have actually built small-scale laboratory simulations of Deutsch's closed time-like curves. Not real-time travel, but quantum circuits engineered to mimic the same mathematical structure, using entangled photons standing in for a genuine loop through time. These simulations, run at universities including MIT and the University of Queensland over the past decade, have confirmed that Deutsch's equations behave exactly as predicted within the artificial system built to imitate them. What they haven't done, and can't do, is prove anything about whether real closed time-like curves made from actual spacetime rather than simulated quantum circuits would behave the same way. Three serious mathematical frameworks then, three genuinely different pictures of what a trip into your own past might actually mean. A universe that quietly edits your actions until they fit, a universe that lets you go but replaces the one you left, or a universe that holds every consistent version of the outcome at once, undecided, until something forces the question to resolve. Nobody knows which one, if any, describes anything real. All three remain exactly what everything else in this stretch of the episode has been. Rigorous, self-consistent, and completely untested against the one experiment that would actually settle it. Completely untested against the one experiment that would actually settle it. Not every hint of backward causality in physics is quite so speculative, though. And this next one, unlike most of what you've heard so far tonight, isn't waiting on any future engineering at all. One experiment, run for real, repeatedly, since the late 1970s, produces results that look disturbingly like a photon, retroactively deciding what it already did. And this one isn't hypothetical. It's been done in laboratories, with results published and independently confirmed many times over. Physicist John Wheeler proposed the core idea in 1978, now known as the delayed choice experiment, building on the classic double-slit experiment familiar from any introductory physics course. Fire single photons at a barrier with two slits, and if you set up a detector to observe which slit each photon passes through, each photon behaves like a discrete particle, going through one slit or the other. Don't observe which slit it takes, and the same photon behaves like a wave, passing through both slits at once and interfering with itself on the far side. The strange part isn't that light does both. The strange part is what happens when the choice of which setup to use, particle detector or interference pattern, gets made after the photon has already passed the slits, with no possible way for the photon to know in advance which experiment it was about to be part of. Physicists have actually run this experiment repeatedly since Wheeler first proposed it, most rigorously in a series of tests beginning in the 2000s using photons and, in later versions, single atoms, with the choice of measurement genuinely randomized and made only after the particle had already committed to its path. Every single time, the result matches whichever measurement was chosen after the fact, not whichever measurement would have made sense given the particle's earlier behavior. Set up to measure particle-like behavior, and the data retroactively looks like the photon behaved as a particle the whole time. Set up to measure wave-like interference instead, and the data retroactively looks like it behaved as a wave the whole time, as though the later choice reached backward and determined which kind of journey had already occurred. Here is the detail that keeps this from becoming an actual time machine, and it's the same detail that keeps quantum mechanics from contradicting relativity anywhere else. Nothing about the delayed choice result can be used to send an actual message into the past. The pattern only becomes visible statistically after comparing many photons' results against a record of which measurement was chosen for each one, a comparison that itself has to wait for ordinary, forward-moving information to arrive. no individual observer gains any usable information before it would ordinarily arrive. The effect is completely real, repeatedly measured, and utterly useless for communication. A distinction physicists lean on constantly when separating genuine causality violations, which have never been observed, from mathematically strange correlations, which have been observed many times over. Most physicists interpret this not as literal backward-in-time influence, but as evidence that photons never had a definite particle or wave nature to begin with, at any point in the journey. That asking what the photon was actually doing between the slits in the detector is itself the wrong kind of question, built on a classical intuition about definite paths that quantum mechanics never actually promised to honor. Retrocausal interpretations exist too, taken seriously by a genuine minority of working physicists, arguing the simplest reading of the data really is that the future measurement shapes the past record. Neither camp has a way to settle the disagreement experimentally, because both interpretations predict exactly the same observable results, down to the last data point. What's undisputed, regardless of interpretation, is stranger than anything a wormhole has managed to produce so far tonight. Unlike every other route toward backward causality discussed in this episode, this one isn't waiting on exotic matter, cosmic strings, or any engineering still stuck on a drawing board somewhere. It's already sitting in ordinary optics laboratories, repeated on demand, confirmed beyond any reasonable doubt. A genuine hint of something backward-looking, hiding in plain sight inside the most thoroughly tested theory in the history of science. A genuine hint of something backward-looking, hiding in plain sight inside the most thoroughly tested theory in the history of science. Sound, rather than light, turned out to be the tool that finally let physicists test one of the most famous unconfirmed predictions about black holes directly, in an actual laboratory rather than waiting for an astronomical observation that might never come. Or that you, watching from Earth, would never live long enough to see confirmed any other way. In 1974, Stephen Hawking predicted that black holes should not be perfectly black at all, that quantum effects near the event horizon should cause them to emit a faint stream of particles, now called Hawking radiation, slowly leaking mass and energy away over timescales almost incomprehensibly longer than the current age of the universe. The prediction reshaped how physicists think about black holes. It has also never been directly observed in space, because for any black hole of stellar mass or larger, the predicted radiation is far too faint to detect against the background of the universe, even in principle with any instrument currently imaginable. In 2016, physicist Jeff Steinhauer at the Technion in Israel built something that let him test the underlying mechanism anyway, without needing an actual black hole at all. He cooled a cloud of rubidium atoms to a fraction of a degree above absolute zero, creating a Bose-Einstein condensate. A strange state of matter where thousands of atoms behave as a single coherent quantum entity, and then engineered a point within it where the flow of the condensate itself exceeded the local speed of sound. Beyond that point, exactly the way light cannot escape a black hole's event horizon, sound waves within the condensate could not propagate back upstream. He had built, deliberately, an analog event horizon, not for light, but for sound. The mathematics governing sound waves trapped behind this artificial horizon turns out to be structurally identical to the mathematics governing light trapped behind a real gravitational event horizon, a correspondence physicists had recognized since the 1980s, but never had the technology to actually test. Steinhauer's experiment let him look for an analog of Hawking radiation directly, and he found it. Pairs of sound wave excitations, spontaneously appearing at the analog horizon, correlated with each other in exactly the pattern Hawking's original 1974 calculation predicted for particle pairs at a real event horizon. He confirmed the result again, with tighter measurements, in a follow-up study years later, ruling out simpler explanations for the correlation. None of this proves real astrophysical black holes emit real Hawking radiation. The analog experiment tests the underlying quantum mechanism, not gravity itself, since a sound wave horizon in cold atoms and a light-trapping horizon around a collapsed star share their mathematics without sharing their physical cause. But it's the closest anyone, including you, will likely ever come to watching one of Hawking's most famous, least testable predictions actually happen. In a lab, on a tabletop, using rubidium atoms instead of a collapsed star 40 times the mass of the Sunday, it's also, quietly, a rebuttal to any impression tonight's episode might have given that every strange prediction in this field simply sits forever on a chalkboard, waiting. Some of it does. The chronology protection conjecture, the exotic matter requirement, the cosmic string time machine, genuinely untestable with any technology remotely available today. But not everything discussed tonight belongs in that category. Some of the strangest mathematics, general relativity, and quantum mechanics have ever produced together has already been checked, patiently, carefully, on a tabletop, by someone willing to build a black hole out of sound, instead of waiting for the universe to hand over a real one. Someone willing to build a black hole out of sound, instead of waiting for the universe to hand over a real one, step back from wormholes and closed loops entirely. And a much older, much stranger question has been sitting underneath this entire episode from the very first minute. Why does time seem to move in only one direction at all? For you, personally, every single day of your life, regardless of what the equations of relativity say, is technically permitted. Here's what makes the question genuinely difficult rather than merely poetic. Almost every fundamental equation in physics, Newton's laws, Einstein's relativity, the core equations of quantum mechanics, works exactly the same whether you run time forward or backward. Film a single collision between two billiard balls, play the footage in reverse, and nothing about the reversed footage violates a single law of motion. The balls could have bounced apart just as easily as they could have bounced together, as far as the underlying physics is concerned, and yet two billiard balls spontaneously arranging themselves from a scattered position into a returning, colliding pair is not a sequence anyone has ever actually recorded. The forward direction and the backward direction are equally legal on paper. Only one of them ever actually happens. The physicist Ludwig Boltzmann worked out why in the late 1800s, and the answer turns out to have nothing to do with time itself being asymmetric at the fundamental level. It has to do with probability. A cup of hot coffee cooling in a cold room isn't obeying some special law that only runs one way. It's simply moving from a highly improbable, highly ordered state, all its heat energy concentrated in one place, toward one of the astronomically larger number of disordered, spread-out states available to it. There are vastly more ways for that heat energy to be spread randomly through the room than there are ways for it to stay concentrated in the coffee. Nothing forces the process to run that direction. It's simply overwhelmingly, almost unimaginably more likely to. Physicists call the measure of that disorder entropy, and the rule that entropy tends to increase over time is called the second law of thermodynamics. Scale that logic up, and it explains an enormous amount about why your own daily life only ever seems to run one way. Glasses shatter far more easily than they reassemble. Ink disperses through water far more easily than it regathers into a single drop. Every one of these processes is, technically, reversible under the underlying laws of physics. And every one of them is so staggeringly improbable in reverse that not a single instance has ever turned up in the entire history of careful observation. Your own body runs on the exact same principle, at a scale small enough to feel personal. Every breath you take increases the entropy of the universe by an almost incomprehensibly tiny amount. Organized, complex molecules in your lungs interacting with air, dispersing energy, nudging the total disorder of everything just slightly further along. The same one-way slope that coffee, ink, and shattered glass are all sliding down together. You have never once taken a breath that decreased the total disorder of the universe. As far as anyone has ever measured, nothing alive ever has. Nothing alive ever has. Follow that same one-way slope far enough into the future, past every human lifetime, past every civilization that will ever exist, and it doesn't level out or reverse. It leads somewhere specific, a state physicists call heat death, or maximum entropy, where energy has spread out so completely and so evenly that nothing remains concentrated enough to do anything at all. No temperature differences left to drive a process, no fuel left in any star, no possible mechanism left for change of any kind. Only a thin, cold, featureless equilibrium stretched across a universe, expanding forever into darkness. Every star still burning tonight is, in this sense, a temporary interruption of that eventual outcome, a pocket of extreme order, nuclear fusion holding back the spread of disorder for billions of years, buying time rather than avoiding the trend entirely. Every sunrise you have ever watched was, quietly, a fusion reaction spending down a portion of that borrowed time on your behalf. Whether or not you ever thought of it that way, the sun itself has perhaps 5 billion more years of that borrowed time left, currently converting roughly 600 million tons of hydrogen into helium every single second and losing a small fraction of that mass as the light and heat that make anything on Earth possible at all, and the several seconds surrounding it that your own mind is currently treating as now. The last, faintest red dwarf stars still burning anywhere in the universe, the slowest and most efficient furnaces nature ever builds, are expected to sputter out somewhere in the range of 100 trillion years from now, a number so far beyond ordinary human timescales that the phrase 100 trillion years barely functions as information at all, more a gesture toward incomprehensible scale than an actual quantity anyone could hold in mind. After the last star, in the extraordinarily long era that follows, current physics suggests even matter itself may not be permanent. Some grand unified theories predict that protons, the particles at the core of every atom, decay eventually, however, astronomically slowly, with experiments searching for proton decay having so far found nothing, setting a lower limit on the proton's lifetime at longer than 10 to the 34th years, a number that makes the age of the universe itself, a mere 13.8 billion years, look almost instantaneous by comparison. None of this is a threat to you personally, or to anyone alive today, or to the next several trillion generations of anyone. It's simply where the same slope you're standing on, the one carrying every ember dim, every current still, your memory forward instead of backward, eventually, unavoidably leads, given enough time. The universe is not indifferent to you by malice. It's indifferent the way a slope is indifferent to whatever happens to be rolling down it. Everything alive is a brief, local, magnificently improbable exception to a rule the rest of the universe is already quietly obeying. Picture the exception in reverse. For a moment, because the image is worth holding on to before moving past it. A glass falls from a counter, and instead of shattering across the floor, the countless fragments already scattered there rise together, spinning faster as they approach each other, edges finding their exact original partners with perfect precision, the whole shape reassembling itself in mid-air, landing gently back on the counter's edge without a single crack remaining. Every individual physical interaction inside that impossible scene would be, on its own, completely legal. Each fragment's motion, reversed, obeys Newton's laws exactly as well as it did moving forward. There's no law of physics that any single shard would be breaking by flying upward instead of falling. What makes the whole scene impossible isn't any individual rule. It's the sheer, staggering improbability of every fragment's reversed motion happening to align simultaneously into the one specific configuration that reconstructs the glass out of the astronomically larger number of ways those same fragments could simply keep moving in whatever random directions momentum happened to leave them. Try to picture the reverse of an ordinary morning, and the same impossible precision would need to run through absolutely everything. Everywhere, all at once. Coffee vapor gathering itself back down out of the air and into a cup. Toast turning back into bread, then into raw dough, then into flour and yeast, unmixing themselves in exact proportion. Your own footprints lifting themselves back off a damp floor and returning the moisture to your skin, molecule by molecule, in precisely the pattern needed to leave the floor exactly as dry as it started. Nothing about any single step is forbidden. The odds against all of them happening together in the correct order are so large that unlikely stops being an adequate word for it. Closer, in scale, to the odds of every page of every book ever printed spontaneously rearranging itself into a single, coherent new novel, all at once. Physicists sometimes call this the statistical arrow of time, to distinguish it from the deeper, still unsettled question of whether time has a built-in direction at the most fundamental level. The statistical arrow doesn't require anything exotic. It only requires that the universe started somewhere highly ordered and has been wandering, ever since, into the much larger space of ways to be disordered. The same reason a shuffled deck of cards never spontaneously sorts itself, and the same reason your own room tends to drift toward mess rather than order unless something, or someone, keeps actively working against the drift. This is the part that quietly resolves a mystery you might not have noticed you were carrying. Human memory only ever seems to work in one direction. You remember yesterday, never tomorrow. And physicists increasingly think this isn't a separate mystery from the shattered glass at all, but the exact same one, viewed from the inside. Forming a memory means physically rearranging matter in your brain into a new, more specific, lower entropy configuration, one that correlates with a past event. Doing that in reverse, remembering an event before it happens, would require exactly the same astronomically improbable, spontaneous ordering that a self-reassembling glass would require. Your memory faces the same one-way slope as the coffee cup and the broken glass. It simply happens to be the slope you're standing on, from the inside, calling it the difference between what already happened and what hasn't happened yet. Calling it the difference between what already happened and what hasn't happened yet. Neuroscientists have found something that fits disturbingly well with the physics you just heard. Using brain imaging, researchers, including psychologist Daniel Schachter and his colleagues at Harvard, discovered that remembering a specific past event and imagining a specific future event activate almost exactly the same network of brain regions. The hippocampus, prominently, along with several areas collectively known as the default mode network. Your brain doesn't appear to have two separate systems, one for memory and one for imagination. It seems to have one system, used both to reconstruct what already happened and to construct what hasn't happened yet, assembled from the same stored fragments of past experience either way. This explains something that might otherwise seem strange. Why imagining next year's vacation and remembering last year's vacation feel like such closely related mental acts, both vivid, both detailed, both drawing on the same store of sensory memory to build a scene. It also explains something stranger still. Patients with severe damage to the hippocampus, who lose the ability to form new long-term memories, frequently lose the ability to vividly imagine their own future in the same stroke. Asked to picture next week, they report something closer to a blank or a vague fragment, rather than an actual scene, because the same machinery that would normally build a specific future is the machinery that was damaged. And yet, for all that overlap, one asymmetry never breaks. In any patient, in any brain scan, in any laboratory anywhere, a specific, confident, verifiably accurate memory of an event that hadn't happened yet simply doesn't turn up, no matter how carefully anyone has ever gone looking for one. Confidence about the future stays probabilistic, hazy at the edges, revisable the moment new information arrives. You can dread a diagnosis, plan for a wedding, brace for a difficult conversation, but you cannot recall any of them with the same settled, unrevisable certainty you'd recall what you ate for breakfast. The past feels finished. The future, no matter how vividly imagined, never quite stops feeling provisional. A quiet, constant background sensation most people never stop to name, felt every single time a plan gets revised, a guess gets updated, or a confident prediction quietly turns out to have been wrong. This asymmetry shows up early in human development too. Children reliably develop the ability to accurately recall specific past events years before they develop the ability to coherently imagine specific future ones. Researchers studying childhood cognition have found that detailed, episodic future thinking doesn't fully mature until somewhere around age 4 or 5. Arriving well after a child can already describe, in some detail, what happened yesterday. The brain appears to need practice reconstructing the past before it can even attempt to construct the future, as though imagination itself were memory's later, less certain invention. Physicists studying the entropy-driven arrow of time and neuroscientists studying memory arrived at oddly parallel conclusions from completely different directions, decades apart, without much overlap between the two fields. Entropy explains why a physical record, a photograph, a footprint, a brain's own neural connections, can only ever correlate reliably with the past, never the future. Because building any accurate record requires the same improbable, energy-consuming, order-creating process that runs in only one direction. Memory, in other words, isn't a window looking freely in both directions a long time. It's a footprint, and footprints only form behind you, never in front. Footprints only form behind you, never in front. Physics has its own definition of now, vanishingly thin, a single instant with no measurable duration at all. Your own nervous system disagrees entirely and has never once operated on physics's terms. Psychologists studying time perception, going back to the philosopher and psychologist William James in the 1890s, use a specific term for the now your brain actually experiences, the specious present. A felt duration wide enough to hold several seconds of experience together as a single, continuous now, rather than an infinitely thin instant. Modern researchers, including the German neuroscientist Ernst Puppel, have measured this window directly, using a range of experiments, tapping rhythms, ambiguous images that flip between two interpretations, brief flashes of sound and light, and arrived at a strikingly consistent figure across many different tasks and many different people. Your felt now lasts somewhere around 2 to 3 seconds. Everything your brain gathers within that 2 to 3 second window gets bundled together and delivered to your conscious awareness as a single, unified present moment, even though the raw sensory information arriving during it is never actually simultaneous at the physical level. Light reaches your retina and gets processed at a different speed than sound reaches your eardrum and gets processed. Touch signals from your feet take measurably longer to reach your brain than touch signals from your face, simply because of the extra distance the nerve impulse has to travel. Your brain quietly edits all of this into a single coherent now, smoothing over gaps and lags that would otherwise make your own body feel like it was arriving in installments. This is, in its own modest way, a distant cousin of the relativity of simultaneity you already learned about earlier tonight. A reminder that now was never a simple, given fact, even before Einstein complicated it at a cosmic scale. Your nervous system had already been quietly constructing its own version of now, stitched together from signals arriving at different times from different parts of your own body, long before anyone worked out that two people on a train platform could disagree about it too. Musicians and athletes live inside the edges of this window more consciously than almost anyone else. A conductor cueing an orchestra, a batter tracking a pitch, a dancer catching a beat. All of them are operating within a present moment, stretched wide enough to feel like more than an instant, narrow enough that missing it by even a few hundred milliseconds registers immediately as being late. The specious present isn't a flaw in human perception. It's the actual working unit your consciousness is built from, the smallest slice of time your mind is capable of experiencing as happening, rather than as memory or anticipation. Which means that even setting aside every equation discussed tonight, gravity, velocity, wormholes, entropy, you have never once in your entire life actually experienced a true physicist's definition instant. Every now you've ever consciously lived inside has already been a few seconds wide, quietly assembled, quietly edited, quietly handed to you as a single continuous present. The only kind of now a human nervous system has ever actually been able to offer. The only kind of now a human nervous system has ever actually been able to offer. Nearly everything discussed so far in this stretch of the episode treats time's one-way arrow as something that emerges from probability, rather than something built into the fundamental laws themselves. Entropy increasing not because any law demands it, but because disorder is simply more common than order. For decades, physicists assumed this was the entire story. And if you'd asked most of them before 1964, they would have told you the deep laws are perfectly symmetric in time, with only statistics making the universe look one-directional. In 1964, physicists James Cronin and Val Fitch found a small, precise exception, working with a short-lived particle called the neutral kaon. Studying how kaons decay, they discovered a tiny but unmistakable asymmetry, a measurable difference in how often certain decay processes happened compared to their exact time-reversed counterparts, a violation of what physicists call CP symmetry, the expectation that physics should look identical if you simultaneously swap every particle for its antiparticle and flip the whole system like a mirror image. The violation Cronin and Fitch measured was small, affecting roughly 1 in 500 kaon decays. But it was real, repeatable, and completely unexpected. It won them the 1980 Nobel Prize in Physics, 16 years after the original measurement, once the physics community had fully absorbed just how strange a result they had actually found, combined with a separate, deeper principle in physics called the CPT theorem, which holds, with extremely strong theoretical support, that the combination of charge, conjugation, parity, and time reversal together must always be exactly symmetric, even when any two of the three aren't. Cronin and Fitch's discovery implies something specific and easy to miss. Since CP symmetry is violated by this tiny amount, time reversal symmetry on its own, T symmetry, must be violated by that exact same tiny amount, just in the opposite mathematical direction, to keep the combined CPT symmetry intact. This is a different and much smaller effect than the entropy-driven arrow of time discussed earlier, a fundamental, microscopic asymmetry, sitting directly in the laws of particle physics themselves, rather than emerging statistically from probability. Physicists have since measured this direct time reversal violation more directly, in experiments at Fermilab and CERN examining subtly different kaon decay rates, depending on which direction, mathematically, the process runs. The effect remains tiny, confined to specific particle interactions involving kaons and, in later experiments, B mesons. Nowhere near large enough to explain why your coffee cools or why glasses don't reassemble themselves. Entropy remains overwhelmingly the dominant reason your daily life only runs one direction. What the kaon experiments prove instead is smaller and, in its own way, stranger. Time's arrow isn't purely a statistical illusion, layered on top of perfectly symmetric underlying laws. Somewhere down at the deepest level physicists have ever managed to probe, in the decay of a particle few people have ever heard of, the universe keeps one, small, stubborn, unmistakable record of which direction is actually forward. A fact so specific and so easy to overlook that most physics students spend years studying relativity and thermodynamics before anyone mentions it exists at all. Most physics students spend years studying relativity and thermodynamics before anyone mentions it exists at all. There's a deeper problem sitting underneath all of this. One you may already be sensing if you've been following closely. That entropy explains the mechanism of, but doesn't actually resolve, and physicist Roger Penrose has spent much of his career insisting the field takes it far less seriously than it deserves. If entropy has been increasing steadily since the beginning, spreading disorder further and further across the universe with every passing moment, then the universe must have started in a state of almost unimaginably low entropy. A beginning so improbable, so exquisitely ordered, that Penrose has calculated the odds against it arising by pure chance at somewhere around 1 part in 10 to the power of 10 to the power of 123, a number so large that writing out all its digits would require more space than exists in the observable universe itself. Every candle burning down, every wall staying cracked, every memory pointing backward instead of forward, all of it depends on that single, staggeringly improbable starting condition having actually occurred. Physicists refer to this as the past hypothesis, the working assumption, built into essentially every calculation involving entropy, that the early universe simply did begin in this extraordinarily low entropy state without asking too closely why. It functions, in practice, exactly the way an unexamined premise functions in any argument, accepted because everything built on top of it works, and rarely questioned about why the foundation itself looks the way it does. Proposed answers exist, and none of them have achieved anything close to consensus. Some cosmologists argue that cosmic inflation, the extremely rapid expansion thought to have occurred in the first fraction of a second after the Big Bang, naturally produces a low entropy starting state as a side effect of its own mechanics. Though critics note this may simply relocate the improbability rather than explaining it away. Others, including Penrose himself, propose exotic models involving cycles of expansion and collapse, stretching across unimaginable timescales, each cycle somehow resetting entropy back towards zero at its boundary. Proposals that remain mathematically speculative, difficult to test, and far from broadly accepted even among cosmologists who take them seriously. What remains missing, in the decades since the problem was first clearly stated, is a settled, broadly accepted explanation for why the universe's starting entropy was so overwhelmingly, so specifically low. The single fact underneath every clock, every memory, every one-directional process discussed across this entire episode. It sits, unresolved, at the foundation of physics the way a support beam sits underneath a house that has never once been fully inspected. Everything built on top of it seems to work perfectly well, day after day, without anyone needing to look directly at the thing holding it up. We still don't know why that particular beam is there, in that particular shape, instead of any of the astronomically more likely alternatives. And tonight, that's exactly where the mystery gets left. Unexplained, foundational, and quietly holding up everything else you've heard. Quietly holding up everything else you've heard. Which brings this all the way back to where tonight began. Time feels like the one thing in your life that treats everyone the same. It doesn't. And by now you have an entire episode's worth of reasons why. Gravity bends it by an amount measured in a single stacked textbook's height. Speed bends it by an amount that let particles born 15 kilometers overhead survive a fall they should never have survived. Two people walking past each other on an ordinary sidewalk already disagree, faintly, about what now even means on a galaxy neither of them will ever visit. Forward, it turns out, was never really the hard direction. Forward is what happens whenever nothing intervenes, the direction of increasing disorder, the direction every dropped glass, every cooling cup, every one of your own memories already knows by instinct, long before anyone explains the physics behind it. Engineers have already learned to bend it precisely enough to fit inside your pocket, correcting satellite clocks down to the microsecond every single day, whether or not you've ever thought about it once. Backward is the direction that turned out to be legal in the mathematics and absent from every observation anyone has ever made. Wormholes, in principle. A rotating universe, on paper, though not the one we happen to live in. Two cosmic strings, if the energy to move them could ever be found anywhere. A closed loop. Sitting inside Einstein's own equation since 1949, waiting for an engineering solution that has never once arrived. Every single door mathematics has opened toward the past. Some other, less complete piece of physics has shown up, suggesting it might close on its own before anyone could walk through. Maybe that closing is chronology protecting itself, the way Hawking suspected. Maybe it's simply that the specific ingredients required, negative energy in bulk, cosmic strings, a universe built differently than this one, have never happened to exist here. In the one universe available to check, nobody currently knows which. What tonight's entire investigation actually reveals, underneath every equation and every experiment, isn't really a verdict on whether backward time travel is possible. It's a portrait of exactly how strange the forward direction already is. Once you stop taking it for granted, a direction so thoroughly engineered, so precisely measured, so quietly present in every clock, every breath, every dropped glass that stays broken, that it never occurred to most people to call it travel at all. You have been moving through time at your own particular rate, shaped by your own particular height and your own particular speed, since the moment you were born. Nobody has ever caught you standing still, not for a single second. Of the many billions you've already spent, drifting forward through the one direction the universe has ever been willing to hand anyone for free. The same direction every clock in your house is quietly measuring right now. The same direction your own next breath is already moving toward. Whether or not you're paying it any attention at all, we've drifted through a body that ages unevenly, one heartbeat quietly ahead of the next. We've climbed into altitudes that rewrite a lifetime without ever announcing themselves, and circled the edge of a collapse so complete it once had another name entirely. We've followed a question about the past as far as the mathematics would carry it, and watched that question hand itself over, gently, to an older and stranger one about why forward exists at all. None of it happened to a stranger. It happened to your own head and your own feet, your own breath cooling like coffee in a cold room, your own memory built the way a footprint is built, behind you, never in front. The universe this episode has moved through was never a separate place you were visiting from the outside. It was already running through you the entire time, in gravity and in speed, in the slow, particular drift of your own now. If your eyes feel heavy, let them close. That was always where tonight was headed. Not toward a final answer about the past, but toward this exact, ordinary, unresolved moment, drifting forward at its own unhurried pace, asking nothing else of you. If this felt like somewhere you belonged, leave a comment when you wake up and tell us which direction you'd choose first. If you're still here, still awake, the next quiet universe is already waiting for you. The universe will still be here when you wake up. So will we. Good night.